Hi, this is Alex from devstories.eu. PyTorch Fundamentals, Episode 1 of 18. You write a complex mathematical model in Python, but when you scale it up, it completely chokes your processor. You need to run those calculations on parallel hardware and continuously calculate all their derivatives, but rewriting everything in a low-level language would take weeks. That tension is resolved by the core identity of PyTorch. When you first look at PyTorch, it often feels exactly like NumPy. You create arrays, multiply matrices, and manipulate numbers. This visual similarity causes a lot of early confusion. People assume PyTorch is just another standard math library. It is not. While standard math libraries are built for CPU-bound numerical computing, PyTorch is designed from the ground up to harness parallel hardware and build dynamic computational graphs. The foundational building block of this framework is the tensor. A tensor is essentially a multidimensional array. If you have a grid of numbers representing an image, a sound wave, or a block of text, you store it in a tensor. The critical difference between a standard array and a PyTorch tensor is where that data can live and execute. Tensors can seamlessly move from your computer system memory to a graphics processing unit. Take a massive matrix multiplication. You have two grids containing millions of numbers. If you ask a standard CPU to multiply them, it processes the math sequentially or in very small batches. The process struggles and stalls. Because tensors are explicitly designed for hardware acceleration, you can send that exact same data to a GPU. The GPU contains thousands of small cores designed to execute mathematical operations simultaneously. A massive computation that takes minutes on a CPU finishes instantly on a GPU. PyTorch acts as the bridge, translating your standard Python code into instructions for that parallel hardware. Fast hardware is only half the requirement for machine learning. Training a neural network requires continuous calculus. You need to know exactly how tweaking one variable changes your final output, which means constantly calculating gradients. Doing this manually for a model with billions of parameters is impossible. This brings us to the second pillar of PyTorch, which is Autograd. Autograd is an automatics differentiation engine. When you perform math operations on tensors, PyTorch does not just calculate the final number, it silently builds a map in the background. It records every addition, multiplication, and data transformation into a dynamic computational graph. When you reach the end of your calculation, you simply ask the framework to compute the gradients. PyTorch walks backward through that invisible graph, applying the chain rule of calculus automatically. You receive the exact derivatives for every single parameter in your model without writing any calculus code yourself. Because this graph is built dynamically on the fly, it adapts to your code. If a standard Python loop or if statement changes the flow of your data, the graph adjusts immediately. The true power of PyTorch is not just that it runs fast or does calculus, it gives you the execution speed of a supercomputer and the mathematical rigor of an automated calculus engine entirely hidden behind readable, ordinary Python. If you want to help keep these episodes coming, you can search for devstories.eu on Patreon and support the show. That is all for this one. Thanks for listening and keep building.